Hello, students. We start today to talk about one of the most important parts of our study of limits, and this is the last part of limits. We're talking about continuity, and our essential question for today is, what do we mean when we say that a function is continuous at a point A? So, continuity. We know that the limit of a function as x approaches a can often be found simply by calculating the value of the function at a. For most functions we have seen already, we can just find the limit by putting the a value in the function. For most functions, but not all functions. The functions with the property in which you can just put the value of a in the function and get the limit are continuous functions at the point A. They are continuous at A. You will see that the mathematical definition of continuity corresponds closely with the meaning of the word continuity in everyday language. A continuous process is one that takes place gradually without interruption or abrupt changes. So maybe it's the first time you encounter the word continuity in mathematics, but it's going to be almost the same as what you see in everyday language. So, continuity at a point. We say that a function is continuous at any number a if the limit as x approaches a of f of x is equal to f of a. So if, just as we explained in the previous slide, if you can just find the limit by putting the value a in the function, then the function is continuous at the point a. When you solve problems on continuity, you will see that there will be three conditions you always have to test for to show that a function is continuous or not continuous at some point. The first condition is that the value of the function at a exists, f of a exists and is defined. Or in other words, a is in the domain of f. Our second condition is that the limit as x approaches a of f of x exists. In other words, the limit from the left and the limit from the right are equal. And three, the limit as x approaches a of f of x is equal to f of a. The limit is just the value of the function at that point. Says that f is continuous at a if f of x approaches f of a as x approaches a. This is just what this third sentence is saying. That f is continuous at a if f of x approaches f of a as x approaches a. Thus, a continuous function has the property that a small change in x produces only a small change in f of x. This may not be too important. The most important thing you need on this slide is these three conditions to test for continuity at a point. If f is defined near a, in other words, f is defined on an open interval containing a, except perhaps at a, we say that f is discontinuous at a, or that f has a discontinuity at a if f is not continuous at a. So if a function is defined near a, but it does not satisfy those three conditions that we had in the last slide, then we would say that there is a discontinuity at a, or that it is discontinuous at the point a. Physical processes, many physical phenomena will usually be continuous. For example, the displacement or the velocity of a car varies continuously with time, and a person's height varies continuously with, say, age or time. But discontinuities do occur sometimes in daily life in electric currents, if you will study electricity in physics, you will see that discontinuities also do occur. So, discontinuity on an interval. A function is continuous on an interval if and only if it is continuous at every point of the interval. So if we have an interval, say from A to B, and we say a function is continuous on that interval, it means the function is continuous at every point on that interval. Remember those three rules test for continuity at a point. Sometimes in calculus we will just say that a function is continuous. If we say that a function is a continuous function, it means that the function is continuous on every point of its domain. On every point of its domain. So geometrically, you can think of a function that is continuous at every number in an interval as a function whose graph has no breaks in that interval. In other words, the graph can be drawn without picking up your pen. I would like to give an example here. If I can draw, let's say the point A and the point B are here. This is an interval, and we say a function is continuous on this interval. It means that I can draw the function without lifting up my pen on this interval. So this function is continuous. But if I draw another function like this, I reach here, I pick up my pen and continue like that. This function is not continuous on the interval AB because it is not continuous at this point. You see, you picked up your pen at this point. You can also have a function that is discontinuous on this interval like this. This function is also discontinuous on that interval. Example, we will look at this figure and find out which points the function is discontinuous and explain why they are discontinuous. We will see that at the point x equal 1, there is a hole. This means the function is not defined. Remember the three conditions of continuity. The function should be defined at the point A, but the function is not defined at the point 1. So it is discontinuous at the point 1. At this point 3, f of 3 exists. F of 3 is this value here. But the limit as x approaches 3 from the left and from the right are not the same. So it means that the limit as x approaches 3 does not exist. Therefore, the function is also discontinuous at the point x equals 3. At the point 5, the function is defined. This is the value of the function. The limit as x approaches 5 exists. From the left and from the right is the same. But the limit is not equal to the value of the function. The limit is this value. But the function's value is this. So it is also discontinuous at x equals 5. So here is another way to explain the solution. There is a discontinuity at a equal 1 because the graph has a break there. The official reason that there is a discontinuity is that f of 1 is not defined. Second, the graph also has a break at a equal 3, but the reason for the discontinuity is different. F of 3 is defined, but the limit as x approaches 3 of f of x does not exist because the left and the right limits are different. So f is discontinuous at 3. And finally, at x equals 5 or a equals 5, f of 5 is defined, and the limit as x approaches 5 of f of x exists. But the limits from the right and from the left, the limit from the right and from the left are the same. So the limit exists, but the limit is not equal to the value of the function, so it is discontinuous at the point 5. Sometimes we will also talk about continuity from the right or continuity from the left. A function is continuous from the right of a number a if the limit from the right is equal to the value of the function. So if you have the point a here and this function here comes to here, the limits from the right is the same as the value of the function at that point. So the function is continuous from the right. But if you have some function like this, if there is a hole there, the limit from the right is not equal to the value of the function. So it is not continuous from the right. It is also continuous from the left if the limit from the left is equal to the value of the function. Think about left. I'm not going to draw left. So there is a worksheet below this video. Please download the worksheet and solve it. Also, there is a quiz, an online quiz below. Take that quiz to practice more for your examination. Thank you.